All right, here we are, Algebra 2, Section 2.6. This is one section before the last section in this chapter. And Section 2.6 is probably one of the more challenging ones. So I'm going to ask you to pay attention. This video will be longer than I'd like, but that's okay. So we're going to talk about special functions. And so let's go ahead and look at our vocabulary. Our vocabulary today starts off with the idea of a step function. And a step function will be any function whose graph would be written as steps, like this. And so what situation would we have a situation where we get these kind of steps? And one is like working or parking your car in a metered parking lot. So what we notice here is that this axis, the x-axis, refers to the number of hours that the car is parked, and the cost is here, and I'm going to say that this is in dollars. I'll just use a dollar sign here to indicate that. And so what we see is that if we park for a half hour up into that half hour point, right, it's going to be $4. So as soon as I set fit in there, it's going to be $4 up until a half hour. If I can get out before a half hour, I'm good to go. But as soon as that half hour clicks in, boom, my price goes up to $5. You guys see that? As soon as I spend an hour in there, boom, my price goes up to $6. $6 is the price if it was for an hour and 15 minutes, because this looks like since this is going to be like 30 extra minutes, so this is like 1.5 hours. So if it was an hour and 15 minutes, right, which would be like 1.25, it's still $6. But as soon as I get to an hour and 30 minutes at this particular parking garage, boom, the cost goes up again to $7, right? So this would be a step function. Step functions often refer to cost, often refer to pricing of things, often refer to, you'll see problems like this that deal with like cost per minute when you're using a prepaid cell phone or something like that. So that's what a step function looks like. The next thing we need to talk about is the greatest integer function, which happens to be a step function. So the greatest integer function is often written like this. Y is equal to like this double brackets around the x. Sometimes it's called a floor function. Also, because we know function notation is what it is, sometimes the greatest integer function can be written as f of x is equal to this thing. This is like the parent graph of all greatest integer functions. So what does it mean? You are mapping the greatest integer that is less than or equal to the value of x. I know that didn't make sense. Nobody gets it. Shoot, I didn't get it when I first heard it. I don't think I heard it 9 times when I heard it. What are you talking about? So we're going to do a table, and then I'm going to give you kind of an analogy to think about it. So if I had some values, x values, you know how we can generally pick random x values. So I'm going to pick some x values from 0 to 3. So 0 is a cool one. 0.5, 0.75, 1, 1.2, 1.7, 2, 3, let's do 2.3, 3.1, I should stick 3 in there and 2 in here. All right, so we got all these values. Let's figure out what's going on. This function says f of x is equal to the greatest integer of x that is equal to or less than x. So is this an integer? Is 0 an integer? Yes. So what is the greatest integer that is equal to or less than x? Equal to would be 0. Let's try 0.5. Is 0.5 an integer? No. So what is the greatest integer that's equal to 0.5? Well, it's not. There is no integer. Or less than that. Oh, that's still 0. So when I'm 0, when x is 0, y is 0. When x is 0.5, y is 0. When x is 0.75, you got it. This is not an integer. So the integer that is closest to this guy, that is less than this guy, is going to be 0, not closest. And as soon as we get to 1, 1 is an integer. So the greatest integer that is equal to or less than 1 is 1. And then 1.2 would also be 1. And 1.7 would also be 1, whereas 2 is 2. 2.3 is 2, 3 would be 3, and 3.1 is 3. So these are the points that I would be graphing. I'm going to graph it in a second, but I just want to talk about what's kind of happening here. In a sense, it's like, what is the greatest integer that I could round down to if this thing isn't an integer? That's kind of what's happening. So if your x value is not an integer, what's the integer that was right before it? The analogy that I like to use is the birthday function. It only works for the positive side. We'll talk about how it could work for the negative side, but it only really works for the positive side when you think about this analogy. So here's what I like to do. I like to say, okay, and you know how when you have a little brother or a little sister and they want to talk about their birthday or how old they are, little kids often say that they are 1.5 or 4.5 or 5 3/4 and all of that stuff. And maybe even bigger people do that too. So if I had a kid who was 1, and they had to fill out a form saying how old they are. If they just turned 1, the form would say that they're 1. If they were 1.5, they might want to say that they're 1.5, but on the form, if they ask the age, I would say 1. If that child did not turn 2 yet, and in order to get into a program, they needed to be 2 or above, I could not say that they were 1.9, so close to 2. I'd have to say that that child was 1. Only when the child actually turned 2 can I pop up and go here to 2. And so all of the age values in between from 1 all the way up to 2 would be associated with 1. As soon as I get into the 2 range, all of the age values, whether the child is 2.2, 2.3, 2.4, 2.5, their actual age that I'd have to write on the form would be this y-axis, and I would have to say that they're 2 years old until their third birthday, boom, now on this form I can say legitimately that they are 3. So it doesn't matter if the child wants to call themselves 4 1/4, 4 3/2. Oftentimes forms don't allow that to happen, and so we have to just monitor exactly what the age of the child is. If you notice, we got a solid dot here because 1 is 1, and we have an open circle here. The open circle means everything up until you get to 2. 1.9999999 will still be associated with 1 in the y value. Same thing with 2. 2.9999999 is still going to be just 2 years old. And then so we get this function, which is clearly a step function, right? You can see that it's a step function, but it has a specific name. It is the greatest integer function. We can extrapolate this information back down here. If the child was just born, they're 0. If the child is not a year old yet, they're not a year old yet. I can't call them 1. Even if they are 11 months and 15 days, so close to 1 year old, right? So close to 1 year old. So, but I have to do that. I have to put an open circle there. I hope that made sense. We can talk about it later. And then what happens also is that was silly. What happens also is that this idea gets extrapolated backwards. So if I were to think about like -3, -3 is -3. But if I were at this point here, this would be -2 point, let me think, make sure I'm not lying to you, -2.9 or something like that. So if I were to round down to I'm not at -2 yet, but if I were to round back to the integer, the integer that's less than -2.9, I'd be all the way back here until I got to like -2.111111. How are you guys kind of all right? I feel like I'm talking to myself. So this is the greatest integer function. It's weird and unwieldy, but we can talk about it again if it didn't make sense. After that, I think we deserve a break, right? We deserve something good. A constant function is a function that would be written as y is equal to x. Oh no, just lying to you. Constant function is not that function. I apologize. That's the identity function. The constant function, my bad, is y is equal to some number, b. And we saw this back in the day when I was talking about slope. When we talked about slope and I was like, this is a positive slope, this is a negative slope, this one here is a 0 slope, and this one is an undefined slope, and this one always has the form y equals b. Remember that? This is what a constant function is. So this y equals b situation is considered a constant function. So you're always going to have, the graphs of constant functions are always going to be horizontal lines because the function y is equal to b or f of x is equal to some value b. is always going to indicate where my horizontal line. So if B happens to be up here, then it's going to be a horizontal line that actually passes through B, sorry baby, and it's going to be there, or you're going to have a B down here. Wherever the B value is located on the y-axis will have a horizontal line. So that's what a constant function is. Identity function can be written in either of these two ways, and it's probably the most enjoyable function ever, right? Because if you had to do an xy table, y is equal to x. So if x is 1, y is 1. If x is 2, y is 2. If x is negative 0.13, then y is negative 0.13. And the key here that you need to get out of this is really understanding what the look of that function is going to be. So what you have is whatever y is equal to, x is equal to, you get this beautiful diagonal line, and it makes sense because if 1 is the x value, then 1 is the y value, and that's the point that you would get for 1, 1. If 2 is the x value, then 2 is the y value, and that's the point you would get for 2, 2. So that's the thing that you want to remember when you're dealing with an identity function. The absolute value function is very cute too. These functions are written as y is equal to the absolute value of x, or f of x is equal to the absolute value of x. If you notice, it looks a little bit like the identity function, right? Remember that was y is equal to x, or y is equal to the f of x is equal to x. And so you're going to get a similar situation. Let's say we were to do a table and we were to come up with the y values associated with it. I can do like negative 1, 0, 1, 2, and 3, and what's going to happen is the absolute value of negative 1 is 1, the absolute value of 0 is 1, the absolute is 0, the absolute value of 1 is 1, absolute value of 2 is 2, absolute value of 3 is 3. And so what you notice is it looks like the identity function here, but here we have this little thing here. Like, why is this different? Well, because absolute value makes things positive. So what I want to do is kind of investigate what would have happened if I had some more negative numbers. Let's say like negative 2 or even negative 3 in for my x values. If I did that, the similar thing would happen. It wouldn't be the same, it would be exactly the opposite. So what I notice is y in this case isn't going to be negative ever, because y is always equal to the absolute value of something. And also, interestingly enough, we get a really funky shape. Now this side is going to look just like the identity function side, right? Where 1, 1, 2, 2, 3, 3 are the points, right? 0, 0. So we had 1, positive 1, 2, positive 2, and all of these points lined up beautifully. But back here, we're going to have negative 1 and positive 1 pop back up. Negative 2 and positive 2 pop back up. So what you actually get when you're dealing with an absolute value function is a V. You're going to get a V shape. Now this V could move all over the board. It could flip upside down depending on what's going on. But what I want you to keep in mind is when you have absolute value of x in an equation, you're going to be looking for some kind of a bend or a reflex, especially if it's an absolute value of a linear equation like this. The next one we're going to talk about is a piecewise function, which is going to take probably the end of this video to explain. Then we'll start back again with the next video where we'll just mention all of these things. So a piecewise function is kind of like a Frankenstein function. It comes in different parts. So oftentimes when you have a piecewise function, you're going to see that it's written like this: f of x is equal to stuff, right? So it's equal to x plus 1 if x is greater than 0, or 5 if x is less than or equal to 0. And what you'll notice that it'll make sense when I graph it. Just watch this. So what I'm going to do first is I'm going to highlight one in red and maybe highlight the other one in purple. And this just gives us kind of two thought processes about how we can process. So if I graph this, so if we look at this one that is purple, or look at the one that is in red rather, that's kind of like graphing f of x is equal to x plus 1. And then if I look at the purple one, we need to know how to graph f of x is equal to 5. Well, hopefully we know how to graph both of these. To graph this function here, I'm going to, basically I can do xy, or I can start at 1 on my x-axis. My slope is 1, so go up 1 over 1, up 1 over 1, up 1 over 1, and I'd graph this. So this is the red graph. That's what that would look like. And then this one, the purple graph, would be a constant function, something we talked about today. 1, 2, 3, 4, 5, horizontal line over at 5, And that's what we have. So here are the two functions that we have. But a piecewise function is going to take a piece of this one and a piece of this one and stick them together. So the graph that we ultimately want is we only want x plus 1 if x is bigger than 0. So I don't want any of this stuff. I'm going to use this big blotching out marker that I have here. I don't want any of this stuff back here.